Today we're going to discuss combinations, and we're going to compare permutations with combinations. Let us start with a problem that we already know. Okay, and we have Anne, Barbara, and Carl, and Dan. So I will use these letters A, B, C, and D are the members of a school club. In how many different ways can they elect a president and a treasurer? Now, any one of these four students can be elected as president. After this happens, any one of the three remaining students can be elected as treasurer. Thus, there are 4 times 3, or 12 possible arrangements. Okay, and we're going to use the initials to represent the students involved, and we could write these 12 arrangements as follows. And now I've listed all the 12 arrangements. Note that order matters here. The first position is president and the second position is treasurer. So A, B, the ordered pair, and notice that we put them in parentheses when order counts. That's what we do in mathematics. AB is different from BA. AB represents that Anne is president and Barbara is treasurer, whereas BA represents Barbara's president and Anne is treasurer. And we have all these possibilities here. Okay, so that is a permutation. Now let's contrast it with B. Now, suppose we have Anne, Barbara, Carl, and Dan that are still members of the school club. And this time, we're going to ask in how many different ways can they choose 2 people to represent the club at a student council meeting? Okay, now looking carefully at the list of the 12 arrangements given in part A, we can see that AB and BA are 2 different slates for president and treasurer. Sending Anne and Barbara to the student council is exactly the same as sending Barbara and Anne. So these 2 are equivalent for part B. Similarly, we could match up all these duplicates. AC, sending Anne and Carl, is the same as sending Carl and Anne. And AD and BCCB, BD and DB, and CD and DC. So we see here that the possibilities, because order does not matter, we'll put them in set builder notation. We could list them as AB, which is the same as saying BA. We could say BC, which is the same as CB. We could say AC, which is the same as CA, BD, the same as DB, and E. I think that's it. Do I have all 6? 1, 2, 3, 4, 5. I'm missing one. Let's see, what am I missing? AB. Oh, I have AC. Oh, I don't have AD, so I'll put it over here. So we see that there are 6 possible committees we can form with 2 students. Okay, and here order doesn't matter. We call this listing a combination of 4 things taken 2 at a time. A combination of 4 things taken 2 at a time. And the symbol for this is 4C2. We also read this as 4 choose 2. Another way to represent this that you'll see in other math courses is with parentheses, and the 4 and 2 are listed as an array. But 4 choose 2, there's 6 possibilities, half of the number of permutations. So this is equal to 4P2, which is the same as 4 times 3, divided by 2 factorial. So 4C2 is equal to 4p2 divided by 2 factorial, and that gives us 4 times 3 over 2 times 1, and that would give us our 6 possible ways. 12 divided by 2, which is 6. All right, let's take a look at an extension. In how many ways can the students, the same students, Anne, Barbara, Carl, and Dan, can they select a 3-person committee to work on the club's next project? Now, order does not matter in a committee. So let's see. If 3 officers were to be elected, such as a president, treasurer, and secretary, then order would be important and a permutation would be formed. However, a committee is merely a set of people. In listing the elements of a set, order is not important. Thus, a combination is used. Let us compare the permutations and combinations that we will list right now. So if I pick a 3-person committee consisting of A, B, C, which are Anne, Barbara, and Carl. Okay, that is a combination right there. But if I consider it, if I take those 3 people and I want to see how many ways I could form arrange a president, treasurer, and secretary, I would have 6 permutations since order matters. And I've listed all 6 here. Okay, so what I'd like you to do is try filling in the rest. Pause and then fill the rest. So I've listed the combinations forming a committee of 3. And they're ABC, ABD, ACD, and BCD. And again, order doesn't matter. But each of these combinations have 6 permutations. Let's quickly list them. So here I've listed the rest of the permutations. And while there are 24 permutations, 4 times 3 times 2, written as ordered triples, there are only 4 combinations written as sets. For example, in the first row of permutations, there are 3 factorial or 6 ordered triples containing A, B, and C. However, there is only one set that contains A, B, and C, namely the set ABC. Therefore, the number of ways to select a 3-person committee from a group of 4 people is the number of combinations of 4 things taken 3 at a time, written as 4C3 or 4 choose 3, and that is 4P3, just like we figure out the number of permutations, but we have to divide by a factor of 6, which is 3 factorial. And that's the number of ways we could permute each possible combination. So that's 3 times 2 times 1, and that gives us an answer of 4 when we divide through. So let's summarize. In general, for counting numbers n and r, where r has to be less than or equal to n, the number of combinations of n things taken r at a time is found by this formula. N choose r equals NPR divided by r factorial. Okay, and on your scientific calculators, there should be a permutation key that looks like this, and a combination and a permutation key, and similarly this. And that key would help you evaluate N choose R, depending on what N and R happen to be. Okay, and as I said before, sometimes we use this notation, and this is read N choose R. N choose R. Okay, a few little pointers here. Okay, now what I wanted to mention is let's look at what 5C5 would be. 5 choose 5 would be equivalent to ask, if we had 5 students, how many committees of 5 can we form? Well, the answer is 1. Pick all the students. But if we plug this into our formula, 5p5 over 5 factorial, that too is equal to 1. So a generalization, NCN is equal to 1. And think about it in terms of choosing committees. In the same way, if we had 5 people and we didn't want to form a committee, we wanted a committee of no people in there, how many ways could that be done? Well, there is a way. Don't pick anybody. And that's one way. So not picking anyone is considered a method. So we could generalize to this step that NC0 is also equal to 1. Now, let's say we wanted to select a committee of 2 people from a group of 7. So let's do this one. We have 7 people, and we want to select a committee of A, 2 people, and B, 5 people. So I'd like you to pause the video and try these yourselves. Well, for the first one, it would be 7 choose 2, which is 7p2 divided by 2 factorial. That gives us 7 times 6 over 2 times 1. And the answer is 21 ways, since these divide through here. 3. Okay. In the other one, we have 7 choose 5, which is 7p5 divided by 5 factorial, and that would give us 7 times 6 times 5 times 4 times 3 divided by 5 times 4 times 3 times 2 times 1. And we notice that the 5 divides through, the 4 divides through, the 3 divides through, and the 2 goes into the 6 3 times. And the answer would be 21 ways again. So we see something very interesting. We see that 7C2 has the same value as 7 choose 5. In other words, starting with a group of 7 people, the number of sets of 2 people that can be selected is equal to the number of sets of 5 people that can be not selected. Okay, so I think that kind of makes sense. In the same way, what do you think 7C3 is equal to? That would be 7C4, or 7C6 is equal to 7C1. And finally, 7C7 is equal to 7C0, which is the property that we have above here. That if we have a group of 7 people and we want to make a committee of 7, there's one way to make that committee, choose everyone. And if we wanted to pick no one, there's one way, just don't pick anyone. So this is a very important property for combinations. For whole numbers, and notice we're saying whole numbers because we could include 0 here. For whole numbers n and r, where r is less than or equal to n, NCR is equal to NC n minus r. Just like 7 choose 2 was equal to 7 choose 7 minus 2, or 7 choose 5. All right, so let's just summarize here. So here, when we have a set, we have two kinds of arrangements. We've got permutations and we've got combinations. Now, with permutations, order is important. Think of ordered elements such as ordered pairs and ordered triples. And the key word here is arrangement. And arrangement indicates a permutation. And the problem might even be very, very clear by stating order is important. So look out for those words, order and arrangement. So NPR is n times n minus 1 times n minus 2, etc., where there are r factors. And we discussed this before. I'm just going to make this one a little clearer because I don't like the way it looks. Okay, now what about combinations? Combination is n choose r, which we said was NPR over r factorial. So the number of combinations is always less than the number of permutation. Here, order is not important. And think of sets. And the key words here are a committee, or a selection of a group, indicates a combination. Okay, I'm going to just erase this here. Of a group indicates a combination. So the key words for combination are committee, select, and order is not important. So look out for those words. Okay, arrangement, order is always important. And again, we have to write the formula. NCR equals NPR over R factorial. All right, let's take a look at a few problems. But before we look at the next problem, for extra credit, prove algebraically that NCR is equal to NCN minus R. It's a wonderful algebraic proof, so try that by yourselves. Okay, so here we're introducing a little bit of combinations with special conditions. Okay, and I wanted to contrast it with one problem. Suppose we have 10 people in the math department. Okay, how many, A, 4-person committees can be formed? B, Mr. W and Miss B, 2 of the teachers from the math department must be on the committee. And C, Mr. G, 1 of the math teachers in the math department must never be on the committee. So I want you to take a minute, copy this down and think about it. So for the first one, we're choosing 4 people from a set of 10. Order doesn't matter. We have a committee. So that would be 10 choose 4, which is 10p4 over 4 factorial. So we have 4 slots. We count down over 4 factorial. And the 4 times 2 gives us 8. And the 3 goes into the 9 3 times. So we have 30 times 7. This would give us a total of 210 ways. All right, now the next one's interesting. Two math teachers definitely have to be on the committee for sure. Mr. W and Mr. B and Miss B. So how many ways can we pick a committee of 4 now if 2 have been determined? Well, if 2 have already been picked, then there are 8 people to choose from. And we just need 2 more people. So that would be 8 choose 2. So if we compute that, that would be 8p2 over 2 factorial, or just simply 8 times 7 over 2 times 1. And again, the 2 goes into the 8 4 times, and that would give us 28 ways. So if 2 people are already chosen, then the number of ways decrease. Here's an interesting one. Mr. G, who is one of the math teachers, must never be on the committee. Well, if Mr. G can never be on the committee, then we're really choosing a committee of 4 from 9 people. So that's 9 choose 4, and that would be 9p4 over 4 factorial. And if we quickly do this, we have 9 times 8 times 7 times 6 over 4 times 3 times 2 times 1. And again, the 4 times 2 is 8, and the 3 goes into the 6 twice. So we get 9 times 14, and that gives us 126 ways. So these are considered permutations with special conditions. Let's take a look at a few more. Here is a very nice geometry problem. Suppose there are 6 points in a plane, no 3 of which are collinear. How many straight lines can be drawn using pairs of these 6 points? So here, let's make a diagram. Okay, so here I have 6 points, no 3 of which are collinear. So if we look at these, whether we join point A and B, or B to A, only one line exists, namely line AB. Since order is not important here, this is a combination of 6 points taken 2 at a time. So this would be 6 choose 2, which is 6p2 over 2 factorial, and that would give us 6 times 5 divided by 2, and that gives us 15. In fact, we could count them. Let's do that now together. Here's 1. Okay, 2, 3, 4, 5. So that's 5 from here. I'll put a little 5 from A. Then 1, 2, 3, 4. There's 4 here. Now let's do the other vertex. Here, I bet there are 3. Let's see. This is already connected. This is already connected. So that's 1, 2, 3. We see a pattern here. Now from this vertex, I already have 3 of them drawn in. So all I need is, I believe, this one and this one, which is 2. And then finally, the last one is this, which is 1. So if we add them all together, 5 plus 4 is 9, plus 3 is 12, plus 2 is 14, and 1 is 15. So this is a nice geometrical illustration. Let's take a look at another one that's in the context of a word problem. Now, this problem looks very different from the previous one, but they do have something in common. Let's take a look at it. In a small beach club, each cottage has one telephone. If 435 telephone communications involving different phones are possible within the complex, how many cottages are in the beach club? Okay, now this problem, well, think about the previous problem. All those line segments that we drew to connect the points are like connecting the telephone lines. So this problem is the same as asking, I can make 435 diagonals or line segments. How many points can I have? So here we let n equal the number of telephones which are like the dots above that we had, the 6 points above, but we don't know how many there are. And the equation would be that NC2, because we're only connecting one telephone with another line, but we cannot repeat that, is equal to 435. So this is almost like asking, how many dots can I make on my diagram so that when I connect between any two dots, I will have 435 connections? So let's solve this. So we have n times n minus 1, because there are two factors, divided by 2 factorial is equal to 435. So we have n squared minus n divided by 2 is 435. We multiply each side by 2. We get n squared minus n is equal to 870. And lo and behold, we have a little quadratic equation in standard form. It's n squared minus n minus 870 equals 0. The two factors that multiply to negative 870 and add up to negative 1 would be negative 30 and 29. And when we set each of those factors to 0, we reject this one, and the answer is that there would be 30 cottages. So these dots, if we had 30 dots, no two were collinear, we could have made 435 connections. All right, so I thought that was a nice problem. Okay, so let's look at number 6. Suppose we have 5 teachers and 15 students. In how many ways can a committee be formed containing 2 teachers and 3 students? Okay, so this is interesting. So we have to consider the number of ways to select 2 teachers. So to select 2 teachers from the 5 that we have, that would simply be 5C2. And to select 3 students from the 15 students that we have, that would be 15C3. But because we want to select both, we use the counting principle, that word and we multiply the two. So very quickly, I don't want to take time to compute this, but this is a fine answer on your homework. But the answer would be 10 times 455, which is 4,550 ways. All right, so we see the word and. When there are restrictions, we have to consider each one separately and how many are in the population. So looking at the next problem, I'd like you to copy this down. We have 10 boys and 20 girls in a class. Find the number of ways the teacher can select a team of 3 students. Now remember, we want a committee of 3 from the class to work on a project if the team consists of A, any 3 students, B, 1 boy and 2 girls, C, 3 girls, D, at least 2 girls. Okay, so copy this, try it. You could leave your answer in C notation and we could go back and check it together on the next page. So the class contains 10 boys and 20 girls for a total of 30 students. So since order is not important on a team, this is a combination of 30 students taken 3 at a time. So that would be, for part A, it's 30, which is 30p3 over 3 factorial. And that gives us 30 times 29 times 28 divided by 3 times 2 times 1. And of course, we can divide through here. 3, 10, and 2 is 14. So the answer comes out to be 4,060. All right, let's look at part B. Part B says 1 boy and 2 girls. So let's think about it. This is a compound event. So to find the number of ways to select 1 boy out of 10 boys, that would be 10C1. Select 1 boy out of 10. And to find the number of ways to select 2 girls out of 20 is 20C2. Okay. Then by the counting principle, we multiply these results. So this would be our answer. I'll leave the computation up to you. The answer comes out to be 1,900. Okay. Now, part C asks us that the 3 members on this team will be all girls. So there's one way to do this. We're picking 3 girls out of 20. That's really all we need. But if we wanted to look at it as a compound event, we're picking no boys out of the 10. So again, this would be just 20 times 19 times 18 over 3 times 2 times 1. Of course, 10C0 is 1. Put a 1 there. And the answer comes out to be 1,140. And then finally, the last one says at least 2 girls. So the number of ways to select at least 2 girls would be the same as the number of ways to select 2 girls out of 20. Or the number of ways to select 3 girls out of 20. So here, either one is fine. So we have to look at these individually, but we add these two, right? A team of at least 2 girls can consist of exactly 2 girls, which is in part B, or exactly 3 girls, which is in part C. And since these events do not overlap, we add the solutions because we have that magical word or. So this is 20C2 plus 20C3. Oh, miswrote that one. 20C3. Oh, wrong pen. 20C3. So in part B, the answer was 1900. And in part C, the answer was 1,140. And when we add them, we get 3,040 ways. So the word at least is popular in both combinatorics and in probability. At least implies that number plus whatever it takes to get up to the maximum that we have. All right, let's try one more with the same problem. Make sure we have it. So let's look at this other phrase, at most. How many ways can we have at most 2 boys on the committee if the teacher is to select 3 people from the same class? So at most 2 would imply the number of ways to pick 2. So that, and how many boys do we have? We have, well, let's see, I forgot now, 10. So we could pick exactly 10, 2 boys from the committee, but we also pick 1 girl because these have to add up to 3. But we also could pick 1 boy for the committee out of 10, but we have to consider picking 2 girls from the 20. And then finally, we could pick no boys for the committee, and we pick all the girls from the 20 that remained. And because either one of these are the same, either one of these are possible, we add them. So this represents the number of ways to select 2 boys from 10, which implies that we select 1 girl from the 20 because we have a 3-person committee. The number of ways to select 1 boy from 10 and 2 girls from 20. And here I'm going to write down and 1 girl from the 20. And then finally, this represents the number of ways to select no boy from the 10 and 3 girls from the 20. Now, please be very careful with the words at most and at least when it comes to combinatorics and into probability, because they will appear a lot in the future. And take it step by step. And if we ever select a committee with a certain number of people in it, and there are restrictions on the type of people that could be in it, we take each of those number of ways for that particular population separately. All right, let's take a look at one more before we end the lesson today. So this last one is a little different from the others. Sometimes we have to be creative in our solutions. Suppose we had 20 tourists who visited a place, and you're a hotel manager, and you have 5 hotels, and you'd like to register these tourists in 5 hotels so that each hotel would have the same number of tourists. In how many ways can you do that? Well, if there are 20 tourists and you'd like to put them into your 5 hotels, that means that there are 4 tourists per hotel. So we have to consider the cases. For the first hotel, you have your 20 tourists, so you choose any 4 from the 20. Then, once those 4 tourists go into the hotel, there are 16 left over. So for the second hotel, we have to choose 4 out of the 16. And once those tourists go to the hotel, we've taken up 2 of the hotels. There are 8 tourists now that are taken care of. Now we've got 12 tourists left, and we choose 4 of them from the 12 for the 3rd hotel. And we keep doing this. We have 8 tourists left, and we choose 4. And then finally, for the last hotel, we've got 4 people left. We have to choose 4, but that's only one way. We just put them in the last hotel. And that's actually, this is 4, and this is 5th. I got mixed up with my numbering here. So we got 4th and 5th. And by the counting principle, because we're selecting all of these tourists with the word "and," we multiply this result. So this expression would be considered, whatever the value of that expression is, would be the total number of ways under the situation. All right, so that takes care of combinations. And I hope this clarifies any questions that we'll have. We'll look at combinations with probability very soon. All right, have a great day.